Welcome to the Harsh Criticism channel. Right now you're spinning at an incredible speed. For instance, everything from buildings, airplanes, and even you at the latitude of Los Angeles is moving west to east at a speed of 1,280 kilometers per hour. But why? Why do all celestial bodies spin? And more importantly, what would happen if the Earth suddenly stopped spinning? This is a question that every curious person should ask at some point. Why do all celestial bodies spin? It's a wonderful and meaningful question because we could easily imagine a universe where everything remains still. But the universe we live in has conservation laws. For instance, one of the most fundamental properties of objects, energy, and thanks to Einstein, we know that mass, which is a form of energy, must always be conserved. This means that within a closed system that doesn't allow for any exchange of energy or mass, whether you mix 50 grams of water with 5 grams of salt, or completely mix 35 grams of radioactive uranium with 20 grams of neutrons, whatever molecules are formed during the reaction, whether it's a physical, chemical, or nuclear reaction, the mass of the reaction products will be exactly 55 grams, not 54 or 56. In other words, mass and therefore energy are always conserved. But this isn't the only conservation law. There's also the conservation of momentum, a law that's often overlooked or forgotten. However, it's vital for understanding the behavior of moving objects. Momentum is equal to the mass of an object multiplied by its velocity. You can think of it as the measure of an object's motion, or perhaps the grandeur of its movement, because the larger the mass and the faster it moves, the more grandeur its motion has. Think about the 10-kilometer-wide asteroid that collided with Earth and wiped out 75% of all species, along with the dinosaurs. It had quite a grandeur, didn't it? Now compare that with a butterfly fluttering gracefully. There's a difference, right? This difference is what we describe with momentum. You might hear people in business or politics say things like, "We've gained momentum, let's not lose it," which comes from this concept. In physics, there are two fundamental types of momentum. The momentum I just mentioned, which is the product of mass and velocity, is called linear momentum. But in three-dimensional space, objects don't just move linearly along the x, y, and z coordinates. They can also rotate around these coordinates, right? This rotation gives rise to what we call angular momentum. And according to the laws of physics, just like mass and energy, momentum must always be conserved. Therefore, when a rotating object collides head-on with a stationary object, the non-rotating object starts to both move linearly and rotate. Of course, the rotating object's speed decreases proportionally to the mass and radii of both objects, both linearly and angularly. This fundamental knowledge helps us understand why everything in the universe, from Earth, the Moon, Mars, the Sun, galaxies, black holes, and anything else you can think of, keeps spinning. You see, everything in the universe started with the Big Bang, and this event wasn't a perfect uniformity. It contained irregularities. If it had been perfectly uniform, all matter and energy in the universe would have been evenly distributed, and stars and planets might never have formed. But the imperfections that disrupted the uniformity in the seconds following the Big Bang allowed matter to clump together in certain areas, leading to the formation of protoplanetary disks, galaxies, stars, and planets. Another effect of the lack of perfect uniformity at the birth of the universe was that these protoplanets also had angular momentum. They were spinning, not standing still. As these spinning fragments began to come together under gravity, their momentum was conserved, and the newly formed larger objects inherited a certain amount of angular momentum. This is why nearly everything in the universe, with perhaps a few extremely rare and coincidental exceptions, spins. The direction of this spin doesn't have to be specific. It can be in any direction. But objects that form in close proximity to each other generally share similar momentum profiles, which is why many objects spin in the same direction as their neighbors. For example, in the solar system, almost all objects, including the Sun, spin in the same direction that can be described by placing your right-hand's thumb pointing along the traditional North Pole to South Pole direction, with your other four fingers curling in the direction of spin, that is, counterclockwise. There are two exceptions to this rule, Venus and Uranus. Uranus also spins counterclockwise, but it does so with a 97-degree tilt, while Venus spins in the opposite direction, clockwise, with a 177-degree tilt. We don't know exactly why, but collisions during the protoplanetary period might have caused these planets to spin differently, as I explained when talking about the moon's formation. The same applies to planets orbiting stars. For example, all the planets in the solar system orbit the sun in the same direction as the sun's rotation. That is, counterclockwise when viewed from above the North Pole. Even more interesting is that all 8 planets, with a few minor exceptions, orbit in almost the exact same plane. That is, one isn't orbiting at a 90-degree angle to the plane of the other. This commonality is a characteristic of rotating objects, as the gas cloud from which the solar system formed also had its rotation, which flattened out into a disk. Hence, all the planets form roughly in the same plane. We see a similar phenomenon in everyday life. For instance, when you spin a top, it spreads out and flattens due to the centrifugal forces. Similarly, the Earth's rotation causes it to bulge at the equator and flatten at the poles. However, Earth's rotation speed isn't enough to turn it into a disk. But if you were to spin an object at extremely high speeds, the centrifugal force would eventually overcome the forces holding it together, causing it to break apart and flatten. For example, in the video currently on the screen, you can see the moment an apple spins 109 times per second and breaks apart. Notice how each piece continues to spin in the same direction as the original apple due to the conservation of momentum. One of the reasons planets spin around stars and moons around planets is the order that arises from chaos. If, for any reason, the initial protoplanets had been spinning in different directions, the long-term result of this chaotic state would have been that planets eventually ended up spinning in the same direction. That's because protoplanets spinning in opposite directions would collide, and due to these head-on collisions, they would lose most of their speed. Remember from the orbital mechanics video that speed and orbit are closely related. A celestial body with little or no speed has a negligible orbit, if any. Those colliding objects would be captured by the sun's gravity and fall into it. After all the chaos subsided, only planets spinning in the same direction would have remained. This could be different for every system, and we indeed observe that galaxies spinning clockwise and counterclockwise exist in roughly equal numbers. But regardless of the direction, the expectation is that, with some exceptions and coincidences, planets formed in the same system will orbit their stars in the same direction. As I mentioned earlier, this is due to the conservation of momentum. Now that we've understood why everything spins, what would happen if the Earth suddenly stopped spinning? Well, momentum would be conserved, or rather a concept closely related to momentum would come into play: inertia. Remember learning Newton's laws? An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a net force. This is inertia, the resistance of an object to changes in its momentum. When a car suddenly brakes, you continue to move forward, or when it accelerates suddenly, you still feel stuck to the seat. That's inertia. And inertia is not something unfamiliar. It's closely related to the concept of mass. The term mass that we're so familiar with is simply the measure of an object's linear inertia, or its resistance to changes in linear momentum. And that makes sense. Think about the formula F equals sign ma, force equals sign mass x acceleration. You apply a force to an object, and that force tries to give it acceleration, but the larger the mass, the smaller the acceleration, right? So, mass is the measure of an object's resistance to changes in its linear momentum. When we talk about angular momentum instead of linear, the concept of rotational inertia comes into play, an object's resistance to changes in its angular momentum. Since the Earth rotates counterclockwise, from west to east, if it were to suddenly stop, anyone standing at Los Angeles latitude would be flung eastward at 1280 kilometers per hour. Not just people, but everything not firmly attached to the ground. Rocks, cars, animals would be hurled eastward. Even tall buildings would experience immense rotational forces, and most would collapse. The atmosphere, which is rotating with the Earth, would continue to rotate if the Earth stopped, creating winds of 1280 kilometers per hour in Ankara and 1600 kilometers per hour at the equator. To put this into perspective, the strongest wind ever recorded on Earth was 408 kilometers per hour, And even at speeds of 288 kilometers per hour, small and weak structures start to fly. Imagine the destruction caused by winds of 1,000 to 1,500 kilometers per hour, similar to the shock wave of an atomic bomb, but on a global scale. Oceans, lakes, and seas would also be flung eastward by the sudden stop of the Earth, causing massive tsunamis that would flood the western coastlines for about 30 kilometers inland. Even if a few people survived the initial shock, they would eventually drown. Only microorganisms and tiny creatures would survive, and since a day would now equal a year, the 6-month-long day and 6-month-long night would cause extreme temperature fluctuations, making the Earth uninhabitable. But you know what? This will never happen. The amount of force required to suddenly stop the Earth from spinning is incomprehensibly large. This is more of a thought experiment than a real possibility. However, it's interesting to note that over millions of years, the Earth's rotation is gradually slowing down. Tidal forces between the Earth and the Moon are causing the Moon to slowly drift away, taking some of the Earth's rotational energy with it. In other words, every century, the Earth's rotation slows down by about 1.8 milliseconds, meaning days are getting longer. It won't be an immediate change, but over millions of years, this slowdown will continue, and one day, the Earth may stop spinning. But don't worry, by then we'll either have found a way to keep spinning or we'll be living elsewhere in the universe. Stay tuned for more captivating science videos, and don't forget to hit that subscribe button if you want to keep exploring the universe with us.